Right. So this criteria whether the system can be considered as a as a lump system, right? So we have the heat transfer coefficient is given 210 watt per square meter Kelvin. We have thermal conductivity 35 watt per meter Kelvin. The characteristic length, I just take the diameter of the junction, thermocouple junction, and the corresponding byte number is 0.006. So based on this characteristic length, we can consider that our system is a lump system. Um, but we would like to compare with the different characteristic length, right? I'm going to use the differentiation from volume divided by the weighted area, and then I'm going to use the characteristic length based on the radius of the thermocouple junction. Right. So we have three different characteristic length that is used to determine whether our system can be considered a lump system or not, right? Um, the we can use the characteristic length as the radius, and the corresponding byte number is 0.003, or we can use based on the ratio between the volume of the sphere divided by the weighted areas. I mean that the surface of the junction all been assumed uh, is in contact with fluid. Um, and then we get the byte number about 0.001, right? But still, all of these characteristic length is less than 0.1. So the criteria to consider the system is based on this characteristic length. All will be considered as a lump system. Right. We're going to use all of these byte number for this problem. If you're using a definition for the exponential variation of temperature based on this byte number and Fourier number, we would like to compare them all, right? And then see how the temperature ratio will varies. Right. So this is the time history. We describe it based on the non-dimensional parameters. So we have the temperature difference of the body minus the fluid temperature, and the denominator will be the initial temperature difference. So it says that the thermocouple read 99% of the initial temperature difference. So what it means here, we're not going to look at very short time, right? Immediately after we immerse the thermocouple inside the gas stream, we read the reading. It's a blink of eyes, right? This does not use for measurement. It's always referred to when the final temperature is almost reached to the fluid temperature. This is the purpose of the thermocouple, is to measure the fluid temperature. So the temperature of the body should be close to the fluid temperature. So the ratio between these two temperature difference should be approach zero, right? So in the equation, it's already given to you. It's already read 99%. So we have another 1%, so that it can reach to 1, right? So we have 1 minus 0.99, so which is 0.01, 1% more that the thermocouple give the fluid temperature. And the response of this thermocouple is given by the exponential rise, which is a function of Biot number and Fourier number. Fourier number is the defined by the thermal diffusivities times period, after the thermocouple is immersed in the fluid, divided by the characteristic length power of 2, and the alpha is the thermal conductivity divided by density times specific heat. And I made mistake there. Fourier number should be characteristic length power of 2. So again, we have the issue of the characteristic length that we should use, right? So here we're going to try all of them, but you should use the one that you for Biot number. You cannot mix thing around, right? If you fix one value, so you should use the same value for Fourier number. And I will show the calculation in Excel application. Right. Let me see here. Right. There are changes that I made to the earlier images that I sent before. Right. So we have I added here about the thermal diffusivities. I also added the density and specific heat. All are given, except the thermal diffusivity is calculated. So you can find the definition of thermal conductivity will be K thermal conductivity divided by density times the specific heat. So you get about 1.2 times 10 to the power 5 meter square second square. And then we look at the when we know about the non-dimensional temperature difference, which is 0.01, right? So about 1% to reach to the final temperatures. So when we make a logarithmic for that values, we got about minus 4.6, yeah. And then we can get the Biot number and Fourier number, which is about 4.6. And then with the information we get what the Biot number just now we calculated based on the diameters, radius, and the ratio of velocity divided by weighted area. We can see that the Fourier number changed from 767, right? And then when the Biot number is become so small, the Fourier number become greater, about 4,600, something like that. And from the definition of Fourier number, we get the time required when we base the characteristic length based on diameter about 1 minute, and then based on the radius about 30 seconds, right? And if we base on the ratio between the density divided by the weighted area, is about 9.9 seconds. So if you look at the example, the value is about 10 seconds. So right, it's most close to it. Right, how do we know that the value is correct? Right, you can determine that the value is correct when you do comparison with the experimental measurement. So if the experimental measurement show the value is about 10 seconds, so it means that the correct characteristic length will be volume divided by weighted areas. Why there is a changes? Because there is a changes because in this problem we made many engineering assumptions, and one of them we say that a heat transfer coefficient does not vary with time. So there are many possibilities, many factors that cause changes. The value does not match the experimental data. Now, I'm showing you temperature response, time history, right? Time history or temperature response from this thermocouple, and the vertical axis is the non-dimensional temperature difference. We have the thermocouple temperature or the heat transfer system temperature minus the fluid temperature, and then we divide with the initial temperature of the thermocouple minus the fluid temperature. So at the initial time equal to 0 per second, right? We have the initial temperature minus T infinities. So that one value, that ratio gives you one value. So at that time, the thermocouple read 0%, right? 0% of the initial temperature difference. So we are using the characteristic length, the diameter of the thermocouple junction. So it takes about 1 minute to reach to the final temperature, right? Here, the temperature, the thermocouple read 0.01, right? So close to 60. So I'm going to plot the temperature difference when we are using a different characteristic length. So give me time to do that. Right, so we have three temperature history or three response. This chart being calculated based on the analytical solutions, right? We are using a three different characteristic length. The blue one will be the characteristic length will be the diameters. The orange one is the radius, and the gray color based on the volume divided by areas. So you can see the response, the characteristic length based on the volume divided ratio of the volume with the weighted area give a fast response compared to the diameters characteristic for the diameters. And because of this, the rate of temperature changes with time is much more higher. So we expect that the thermocouple will reach to the final temperature, the fluid temperatures, quicker compared to other based on other characteristic length. So you can see that the differences between the points when the thermocouple is first immersed inside the fluid, the temperature changes is quite large. We can see the differences. But as it goes to the final temperatures, the rate of temperature changes it becomes small, and you can't see any differences, between measurements, right? So of course we like to use thermocouple with the fast response compared to the one with the having a large thermal inertia. So in this case, we are looking at the the thermocouples, which is we can represent the fluid temperature is higher than thermocouple, or thermocouple is has a less temperature compared to the fluid.